Hello friends, so now we will study electric currents in conductors. Now an electric charge, it will experience the force if an electric field is applied. So there is a charge placed at the center, uh, the charge placed at the center, there is a charge placed at the center. So it is placed in an electric field, and since it is placed in an electric field, it will experience a force, this F in that field. If it is free to move, it will thus move, contributing to a current. Now in nature, the free charge particles do exist in the upper strata of the atmosphere. So this is the Earth, this is our Earth. So we have seen the upper strata of the Earth is this is the upper strata. This is troposphere, stratosphere, ionosphere, last is exosphere is there. It is the exosphere. Now free charge particles, they exist in this ionosphere layer. However, the atoms and molecules, the negatively charged electrons and positively charged nuclei, are bound to each other, and they are not free to move. They are not free to move. See here, proton and neutron in an atom, electrons are there. They are very closely, they are very charged electrons. They are bound to nuclei and hence not free to move. These are not free to move. They are pulled towards the nuclei, these electrons. And the bulk matter is made up of many molecules. These are the bulk matter. These also made up of many molecules. This is a bulk matter. These are made up of many molecules, and 1 gram of water contains about 10 to the power 22 molecules. These molecules are so closely packed that these electrons are no longer attached to individual nuclei. These molecules are so closely packed. This is a molecule, this is a molecule, this is a molecule, this is a molecule, this is a molecule. So this is the nucleus, and the electrons present it, they are so closely packed that they are now not attached to the individual nucleus. So these molecules are not attached to the individual nucleus. In some materials, these electrons will not accelerate even though electric field is applied. So they are now so tightly packed that even though electric field is applied, electrons will not accelerate even though electric field is applied. Now in some materials, this mostly metals, this is metals actually. These metals, electrons are free to move within the bulk material. This is called conductor. This material develops electric current in them when an electric field is applied. So in a conductor, the material allows electric current to flow through them, and this current is carried by the positive charge electrons in the background, is carried by negatively charged electrons in the background of fixed positive ions. Okay. In electrolytic solution, this positive and negative charges both can move. Now let us suppose a conductor is lying in a place where electric field is absent. No electric field. A conductor is lying out there. Now due to the surrounding temperature, only what happens? Only thermal agitation is present within the conductor. Only thermal agitation due to surrounding temperature. And these free electrons, collide with the fixed charge. These free electrons then collide with the fixed charge present over there. So an electron colliding with an ion emerges with the same speed as before collision. So this is an electron. It is colliding with an ion. It is colliding with an ion. After collision, it emerges with the same speed. The V over here is same as the V over here. Okay. Remember, it's very important. An electron colliding with an ion emerges with the same speed. But what is if the initial speed is u, the final velocity is v, then u is equal to v. Initial speed is equal to the final speed. That is before collision. This is before collision, and this is after collision. Okay. However, only direction changes. See the direction, it is in this direction, and now the direction is in this direction. So what happens? Only the direction changes. On an average, what we can tell, the electrons traveling in one direction equal to the electrons traveling in opposite direction. So what happens when suppose the electrons traveling in this direction, from here electrons traveling in this direction, from here electrons traveling in this direction, from there. So on an average, this net charge is flowing from this side to this side. They cancels other, more or less they cancels each other. So net charge flow is then 0, and hence net current flowing through it is the 0. Okay. So this takes place when there is no electric field, when electric field is absent. But what happens when an electric field is present? Let us suppose this is a conductor, cylindrical conductor, a wire magnified many times. It is placed in an electric field capital E, and two charges are applied on both these sides. One is plus Q and another is minus Q. So let the radius of the conductor be R. The charges plus Q and minus Q are placed at the opposite ends of the conductor or at the terminal ends of the conductor. After some time, electrons will dip because of the electric field created to neutralize the charge. Now electric field, what happens after some time? Electrons will dip because electric field created to neutralize the charge. Means the negative fuses with the positive and the charge is neutralized. So current will thus stop after a while. Okay, this negative charge will be attracted to the positive. So the electrons neutralize and ultimately no current flows through it. But as long as this particular electron move, it will constitute an electric current. Do you agree? Yes. Okay. Now imagine a mechanism where you can continuously supply these electrons stepwise within a very small, infinitesimally small seconds the time. That means there is continuous flow of charge. So if you can keep on giving plus Q and minus Q both the sides continuously, you will be able to get a continuous current. This constitutes an electric current. Okay, so there will be a current continuous flow. Okay. So next part, Ohm's law. Thank you for today. Bye. Stay tuned for the next part, Ohm's law. Thank you.